1981. He obtained his Master's in Forensic Chemistry from the University of Pittsburgh and a Bachelor's in Chemistry from the State University of New York College at Oswego. His work experience includes many years as an adjunct faculty of Virginia Commonwealth University, teaching both graduate and undergraduate level courses, and also mentoring graduate interns. He's currently the mass spectrometer and DART-TOF operator for both the Controlled Substances and Trace Evidence sections in the Central Lab of the Department of Forensic Science. Since 2007, Bob has worked extensively with direct analysis in real-time, time-of-flight mass spectrometry, developing new methodologies for applications in forensic science. Please welcome Bob.
Thank you, Ruth. Thanks for inviting me to come out here today, and I hope you all are having a good time at Pittcon. It's quite a show. All right, first we're going to talk about the DART just a little bit. I'd like to see, we need some audience interaction here. How many people, show of hands, know what direct analysis in real time is and how it works? Awesome, that's awesome. See, so I don't have to tell you all how this works, and those of you who need details on that, come see me later. I'll be around this evening, and certainly right after the symposium we can discuss things like that. So I'm going to kind of dive in. I'll give you a little overview. My talk today is basically skimming slides out of my students' presentations over the last 5 years and putting them all together and giving you an idea of what the projects that we've done and some of the really fascinating things that we've done with our DART source. Chip, if you remember the hotel, that is the hotel. Okay, the Sanibel conference in 2005, which is where Chip Cody presented the DART to the world, and I actually was there at the time, which was pretty fascinating that I actually got to go to a Sanibel conference. Since then, 2005, the direct analysis and real-time source that year won the Pittcon Editor's Gold Award for new innovation, and it really was a very innovative source when it first came out, and it still is. We're seeing other applications of it here at this year's Pittcon. We got ours in 2007. The DART is the blue thing that's sitting there on the front, and it's actually marketed by IonSense. And we have it on a Joel Accutoff time of flight, an accurate mass time of flight. And we had it installed right in early 2007. So since that, I'll give you a little idea of how it works. DART is a direct analysis in real time. It's a soft ambient ionization technique, solids, liquids, gases, however you can deliver it to that ion source, you can typically get some kind of ionization to occur. Having it on an accurate mass time of flight is really nice and it was a real leap of faith for me because I was a nominal mass GCMS guy, single quad LCMS guy for a long time, and the whole accurate mass thing was a real leap for me. So it's been really wonderful to have that, though, to be able to differentiate compounds and empirical formulas. One of the nice things forensically is the last statement at the bottom where the calibration is in every data file. Those of you who are in the field, and if you have to go to court, one of the questions that you always are typically asked is, when was your machine calibrated? And your answer with a GCMS, well, for ours it's every day. We do it once a day. We do an auto tune on our systems. For the DART, I could sit there and I can go, I calibrated it 30 seconds before I ran the sample, because I'll run my calibration, my polyethylene glycol calibration, roughly 30 seconds before I run my sample. So it's really nice to be able to know that your instrument is working really well right at that time. All right, so here's a little, one of my students did this, great graphic. The DART gas, heated helium stream, metastable helium ions coming from our left to right, and going into the orifice of the mass spectrometer. The best sampling technique that we came up with during our validation was to actually do a methanol extract or a solvent extract. We used several different solvents, but to use a solvent extract of the solid material and then dip what we call a wand, but it would be a closed end of a melting point tube into the liquid and then hold it into the DART gas stream. So here's our little wand, and we hold it in the gas stream, and the ions come off and go into the orifice, some of them. Not all of them. Some of them get stuck to the orifice, and but you get enough in there to be able to get an idea of what you've got. And that's extremely helpful. One of the things that we do in our setup and with our screening technique is that we actually change the voltage on the orifice 4 times every second. And by changing that, we can get some collision-induced dissociation to occur, and we can therefore get fragmentation. We can not only get spectra of the protonated molecules, but we can also get spectra that have fragmentation with them. And you'll see some examples of that as we go forward here. All right, so the first, this was summer of 2007, which was a real leap of faith to have a student come in. And I got to tell you, all my students are Virginia Commonwealth University graduate students. Go Rams, watch out for havoc. For those of you who don't know that, watch the NCAA tournament. It's coming up. What? Okay. Mark Bennett came in. Mark was a graduate student at the time, and we've actually since hired him. He works in our Roanoke laboratory now as a drug chemist. And we worked with GHB. We spiked 50 different drink samples, and those ranged everywhere from water to some of Franklin County's finest. And for those of you who are familiar with Virginia, that would be where moonshine is really originated. And we spiked those different drink samples with GHB and looked on the DART. We used negative ion mode to be able to see if we could see the GHB. And here was an example, ocean spray cranberry juice. There's the blank. That would be a negative ion DART spectrum. You can see the sugars in there. And then when we spiked it with GHB, that was a 2 milligram per mil spike. The deprotonated molecule shows up really nicely. And so from that, we still are going to go on and do final GCMS confirmation of that, derivatize it, and then do a GCMS final confirmation. But to be able to have a very simple technique to take a little sample of whatever the drink is, and when the police go in and they suspect that there's going to be some kind of GHB present or date rape type of scenario, they may collect the whole all the drinks off the bar, and we're here now. We've got 40 different bottles of whatever it could be, and we've got to test it. So it's nice to have a really quick screening technique. In this case, we're using the DART. Here's a little bit of more information. The orange bars are the actual spikes in the different types of drinks, and we kind of lumped them together here. And what you see is the blank average way down at the bottom, the little purple bars. And then we had to establish an administrative cutoff because some things like red wines and white wines actually tended to have a little background at that 103 ion where the negative ion of the deprotonated molecule was. So we had to, the administrative cutoff was a little bit higher there. But when we looked at impairment levels and talked to our toxicologists about where we needed to be, looking, and we're going to be way above that if there's actually GHB present in the samples. So that was a fun little project. We published that in J4Sci. And you'll see those go by as we move through here. Suzanne Howlett came in 2009. I don't know what happened to 2008. We were in the middle of validation or finishing validation, and we started using it for casework, and I actually probably had to do casework at some point. So I didn't have a student in that year. So we got to 2009, and Suzanne came in. Suzanne was recently in the ARISE program. I don't know if she's still there or not, but we looked at thin layer chromatography DART, because DART spectra in and of themselves, with having no chromatography in the front end of it, they can be very difficult to interpret the spectra. So we started looking at ways to do a little chromatography beforehand, and TLC was the nice, cheap, fast thing that we do all the time in the lab anyway. So we said, let's try to do just some simple DART stuff. So we looked at tablets, especially acetaminophen codeine tablets, that kind of thing. And so here's a TLC plate, and what Suzanne did was actually laid it on a glass cutter and sliced down through the spot and then sprayed the plate with glycerin, and that helped to bring the drug itself to the surface of the plate. And then she just held that plate in the well, there's actually a better picture back here. Held that in the DART gas stream at a kind of a little bit of an angle, so that you don't want to occlude the orifice as you're doing this. And she was able to get pretty decent results with that, and we actually published that in J4 Sci. Fall 2009, Allison Pfaff, now Allison Weston, I'm not sure where she is. She was working in Georgia for a while, but I'm not sure where she is now. We looked at bank dyes and pepper sprays, and while the bank dye was really cool, the pepper spray was a lot of fun because, when she was doing this, we collected all kinds of hot sauces because we wanted to see about capsaicin in various hot sauces. And people came into the instrument room and went, "Man, you guys making wings back here? This is great." So anyway, the bank dye components, especially the methylaminoanthraquinone, the actual bank dye that is found in the exploding bank packs, we wanted to look for a way to pull that off of clothing. And Allison tried a whole bunch of different things, not the least of which was taking dropping some of the dye on a piece of fabric and holding that in the DART source, and one of those actually melted and occluded our orifice. And that's one of those, good things, bad things. That was one of those really bad things. So we had to kind of resurrect the instrument after that. And one day she was trying to take a swab and actually swab the sample off of the T-shirt that we were doing. And she had that laying on a piece of glass. And, she looked at the swab, and there was hardly anything on the swab. She had soaked the swab with methanol, and there was like hardly anything on there. And she picked up the fabric, and here was on the glass, here was all this red dye. So she was like, "Oh, well, okay." And I said, "You know what, let's try something else." So we got some cardstock that you would use for like an inkjet printer. And we put a piece of that on the glass, put the piece of fabric over that with the dye on it that was dried onto the fabric, and then took a couple drops of methanol and then a piece of whey paper, just so we didn't contaminate it, and just kind of mushed the whey paper through the fabric, and it deposited that spot beautifully onto the cardstock. So the beauty of that is now we have this incredibly nice sampling technique where all she had to do was take where the red dye was on the cardstock, fold that over, and draw that through the gas stream. And if you don't find anything or you want to keep sampling, you fold the cardstock again in another little spot and draw that through, and there you go. Off you go. You have a nice spectrum to work with. So that was a great technique. Another thing that we published. There's a whole bunch of these things. Okay, so Jessica Wood came in. She was my only undergraduate intern, which was really quite special to have that occur. We published this. This was kind of an extension of what Suzanne had started a couple of years before, or the year before. And we looked at, one day we were sitting there and going, we got all these pharmaceuticals in our back cabinet, and we would like to be able to have DART spectra of standards, but so a lot of them were preparations, so the DART spectra were mixture spectra, and they weren't all that great. So we said, well, we could have a student come in and do all the work, which we did. And so Jessica came in and actually took standards and purified them with TLC, scraped the plate, added a little methanol, wanded that in, and all of a sudden now we've got all these great spectra for our library. So that was a great project. Drug testing and analysis, grabbed that one. At the same time, I had Catherine Moore. Catherine works down at RTI now. And, by the way, Jessica is getting her master's in analytical chemistry at William & Mary. Just keep up with my students here. You got to, it's nice to let them know that we keep up after them. Catherine is working down at RTI now. And she's really instrumental in getting the forensic DB going. And if you're not aware of that, I suggest you try to, go take a look at that. All of my DART spectra are on there. All of the AAFS tox library spectra are on there. And then a whole bunch of things, especially syncans and research chemicals and things like that the people at RTI have been running on all their different instruments, and they've been putting spectra on the in the forensic DB. You can go in there. It's a secure website. Go in there, and but it's free to sign up and be able to go in there and search for compounds in there. And there's tutorials and everything on how to use it and play around with it. So here's an example of some of the spectra that are in there and some of the information. The website was designed by ACD Labs, and it's all an NIJ grant that Dr. Peter Stout runs down through RTI International, or RTI. All right. All right, this was a fun one. Casey Mims works for HDL Labs, which is a huge health diagnostic laboratories, which is a huge company that's really just taking over the whole biotech park in Richmond, Virginia. It's a great company. She did a project. We had heard about possibly looking at polymers in gasoline, and it actually originated with Jerry Risbridger in the Forensic Science Services Lab in London. And he had mentioned it, and we said, well, let's give this a try and see what happens. Well, gasoline is gasoline is gasoline. When it's refined and it goes to the big tanks, and at some point there's going to be an additive package put in there, and that additive package is going to be specific to the company that owns the gas station where it's going to be delivered. So you have your typical 8,000-gallon tanker truck backs up to the depot there and gets filled up, and they take a quart of an additive package with whatever polymers are in there to help your engine run better and make sure your emissions aren't as bad. So what Casey did was we looked at could we differentiate gasoline by brand, and that was the grand thought behind what we were doing. By looking at the polymer pattern that results. Well, you can see here's some BP gas from two different locations, one in Raleigh and one in Richmond. And you can see that the polymer pattern is different. The way she did this was actually take a melting point tube, a wand, and deposit 7 microliters of whole gas onto that wand and let that evaporate in the hood, so that we didn't worry at all about the volatile components at the low end. And then we scanned, obviously, we had to calibrate up to 1600, which we used Ultramark 1621, is that? To calibrate the instrument, up to the upper end. And, got really cool results to be able to see these different polymers. Here's Hess gas, 3 different locations. As we'd go around on vacation, I would get gasoline samples, and we would test them. And so here's 3 different Hess gases, and this is one of the big problems with gasoline by brand. Well, they're all 3 from Hess, but you have summer blends and winter blends and regional blends, and depending on where you are. So there's a lot of variation in there. So this was really a great proof of concept. Never published this. Anyone wants to pursue this further, there's always information here, and I can tell you what we did and get you going. But this was a very unique experiment that we did. This was fun. We went out to the parking lot and we took some chunks of carpet and put a couple of mils of gasoline on a chunk of carpet and lit that. And then we did, we just tried to light another piece of carpet as a blank, and then we had a non-lit. So we did all that, and then we looked at the polymer pattern. So we've got A is just the evaporated chevron gas, and then B is the blank carpeting, and then C is your the gasoline after it was ignited. And it's interesting to note that the polymer pattern in C is similar to A, but if you look really closely, the masses are off. But they're all off by the same amount. I think it was 43 Daltons. So very interesting, and we weren't explaining that because we never got really to that point of explaining it. But a really great study, had a lot of fun with that. Emily Lawrence now works in our toxicology section. She's training as a forensic scientist in our toxicology section in Richmond. She came in and we worked with smokeless powders. We actually collected 96 different samples of smokeless powder, and we did plus and minus DART. We did GC, EI, and PCI MS on it, and we did FTIR on those. And she took photomicrographs of all the so we could get the morphology. All this information, once again, we didn't really have enough to publish with this, so but all this information went to the Forensic DB, and I'm not sure if that's published there or not. But just to give you an idea, here's a negative DART spectrum of a smokeless powder. Now this is just a it was a 50-50 methanol methylene chloride extraction. Just take a small sample of the grains of smokeless powder and add the solvent to it, wand it in, and this is what you get. So it's really quick and dirty, and so you see both the negative ion where we could see the nitroglycerin, and then the positive DART spectrum with all the rest of the components that you're used to seeing in your smokeless powders. So that was a pretty fascinating study, and you know, when you combine all of the data, you really start to you can get differences by brand, because a lot of the companies will you know, have different amounts of their ingredients in order to change the propellant properties. But you know, we really couldn't tell that specifically with the DART, but when you started adding in the GC data and the PCI data, things like that, that really helped to give us a little more differentiation. All right, Torquay Torquay's getting his PhD in forensic science down at Florida International University. And he worked with the DART with me here with carpet fibers. And really nice and simple stuff. We have, I don't think we've published this. We didn't publish this. Nylon 6 from nylon 6,6, and you know, we were able to distinguish those quite easily by their DART spectra. Here's some known carpet samples that were actually labeled to what their content was on them. He went to Lowe's and grabbed all these little samples of carpeting for our study. And you know, but one of the most interesting things that came from this was the fact that most of these carpet samples had this peak at 282.2789, that region. And we looked at this and we kept finding this in every single carpet fiber, and we were like, what the heck is this? And we did elemental composition on it, and the best thing that we could come up with was that it was oleamide. And we said, well, oleamide, what, you know, where is that coming from? It's a polyamide, you know, and what we found out is that it's added when the fiber is spun, it's added as a slip agent to be able to, you know, make the fiber come out of the machine properly and give you your fiber. Well, we found a couple studies where someone had actually discovered oleamide, like on an LCMS study of a sample, and they actually attributed it to their laboratory glassware, or labware, I guess it would be. And we started going around. We grabbed every piece of plastic labware we had, and we found oleamide in every stinking one of them. And so now the big problem with that is I've got my chemists, you know, and we use the DART for screening, and you know, they have a pipe and they want to rinse that pipe, and I keep telling them, rinse it into something glass, because otherwise you're going to have that big 282 ion, and it might interfere with something else that might be a drug. And you know, so if someone makes polypropylene labware without oleamide, we might need to start talking. So because that is a bit of a problem. And JWH018 oleamide has been found in samples with some of the Syncans, but you almost have to wonder if it was found because they used plastic labware. So anyways, but it is actually similar to some of the synthetic cannabinoids, so it could actually be attributed to that. All right, Alex is at Indiana University right now, and he is getting his PhD in analytical chemistry. And he came in, he wanted to look at natural test. He's a bodybuilder, so he wanted to look at some of these things. And he actually had some samples. So he brought his stuff in, and we did some testing on it. And truly, unfortunately, we didn't find a whole lot in there in the way of steroids, which was good for him. And we found some other things, you know, in some of these products. But we didn't find anything that we could say was definitely a steroid. So I guess, you know, it was a kind of a good study, bad study. And we actually went on to other things, and that was this part, where we looked at, we had a case that came back. It was in our Northern Virginia region, and there was a court case, and someone mentioned this, an article by Dr. Dale Forrester. I think he was from George Washington University. And he had studied, for his PhD dissertation, he had studied the Duquesnoy-Levene reagent to its umpteen level. And one of the things that he did was he had presented in his dissertation, he had some instrumentation results in there, and we were able to get a copy of that. And it was really some, I mean, in like the mid to late 80s, and the mass spec data wasn't all that great. But he proposed a chromophore for what that nice purple color is that you get in your chloroform layer when you do your Duquesnoy-Levene reagent. And this is the chromophore that he proposed. And I said to Alex, I said, do you think we could maybe try to take that chloroform layer and see if we can find that chromophore? And if we could confirm that, that'd be pretty darn cool. So here it is, the molecular, the protonated molecule at 475.2807 corresponds beautifully with the proposed chromophore. And we actually went over, we took DART data, it was a labor of love to purify that chloroform extract. But he did quite well doing that, so we got the 90-volt DART spectrum, which is the fragmented spectrum. And we took a sample of that over to our triple quad over in Tox, and we begged and borrowed if we could, use their instrument, and they actually let us. And so we looked at the spectra, and it's interesting to look at the fragmentation similarities between the triple quad and then the DART spectra, the fragmentation CID spectra from the DART. So that was pretty cool. The manuscript's in my backpack, so we're working on that. This would have been an awesome DART case we had, several years ago. Before we got the DART, somebody had cleaned out some pharmacist, cabinet, and threw all the pills just into a couple bags, and we had to separate them all. And this is the basically, sort of yellowish to green, or through the reds, and we separated them by color, and then we had to separate them by markings, and this was quite the case. Anyways, Jake Easter came in last summer, and if any of you were at the AAFS meeting just a couple weeks ago, he presented this. So I'm not going to, he's already presented. I'm not going to show you a whole lot about what he did here, but it was actually a great experiment to actually now take the DART to the next level, because instead of just using it for screening, we want to be able to use it as a confirmation tool. And how many of you are familiar with SWIG drug? Oh, come on, we got to have more people. That's the Scientific Working Group for seized drugs. And they lay down all the rules for how you're going to do your analysis. Well, you have to have a category A and a category B or a category C technique in order to satisfy requirements for your mass spectrometry or for your confirmation results. So as it turns out, the markings and the physical identification that you get from the tablet marking, size, shape, and color is a category B technique. And then we were hoping that, well, if you have, a category A technique such as mass spectrometry with enough fragmentation to be able to give you enough information, not just a protonated molecule, but enough fragmentation to give you reproducible results, of fragmented spectra, would that satisfy? And we feel very confident that it will, and we're drawing up protocols as we speak to be able to use this in our casework, because we feel very confident in what we're able to see with this. And we use multivariate statistical analysis, which I didn't show any slides, but we'll let you handle that later. Okay. Anyway, so here's some of the spectra. One of the fun things that we looked at were the codeine isomers. Codeine, hydrocodone are the only two that are actually available in pharmaceuticals. The others, for whatever reason, are not used in pharmaceutical preparations, so we really don't have to worry about them. But it's nice to see that compounds that have the same empirical formula give you entirely different spectra. And our PCA analysis showed this really beautifully. And like I said, I didn't bring the slides. I'm getting close on time, so I'm watching. All right, so here's some fun things one of the fun things that we did with the DART. This was a couple years ago. We were contacted by actually the History Detectives people, Oregon Public Broadcasting, and they had gotten wind of these dolls that were over at the Museum of the Confederacy, which is in Richmond, and we were asked to see if we could determine whether there was any drugs in these dolls. They were supposedly, according to the provenance, when they were donated to the museum, they supposedly were used to smuggle drugs through the blockade to the south from the north, during the U.S. Civil War. So Casey Mims actually did the testing on this, and this was Lucy Ann, and the back of her head was all bashed in, which was interesting. She had her little bonnet on. She looked beautiful. But the back of her head was all kind of caved in. And so we swabbed in there, and we swabbed up inside Nina's head as best we could, you know, these are 50-year-old dolls, for crying out loud. And I was like, I don't want to touch these things, you know. These are really just unbelievable artifacts. And so we tested them, and the question was, what drugs were we looking for? Somebody want to tell me? 2 most important drugs, probably? What? Quinine? No. Civil War, 1860s. Quinine and morphine. How about those? They were probably the 2 most important drugs to the field physicians in the South. You know, because they knew they needed that quinine because malaria was a terrible thing. They didn't understand the whole vector of, you know, mosquitoes and malaria, but they knew that if they took quinine, they could help prevent that. Cocaine wasn't around yet. You know, that was late 1870s or so, what, Vin Mariani and all that. Yeah. Okay. So anyway, so we looked for quinine and morphine, and we actually had, this is Gwen Wright on the left here in the black sweater, and Kathy Wright, no relation. Kathy is the curator of the museum, and Gwen is one of the history detectives, and they came in and we did this entire day of filming for, you know, 5 minutes of airtime. And but the cool thing was we actually got to sample Nina twice, and we did a better job sampling the second time, but unfortunately, we found no drugs. But we had a grand time. I'm on TV. So's Casey. Here we were at the DART. It was kind of cool. Yeah, I know. I'm over. Okay. So now the next thing I'm going to show you, you can't tell anybody about. That's really dumb, isn't it? This is being videotaped. Holy mackerel! All right, we haven't actually put this out to the public yet, but Kathy Wright brought us. Actually, we did this up on the new DART up at VCU, and Chip Cody was there, which was great to have him there to help us interpret the data and look at it. But this little box from Mead and Baker Apothecaries was found in the rucksack of Obadiah Jennings Wise, and he was I think a sergeant at the time in the Richmond Rifles at the Battle of Roanoke Island in eastern North Carolina in 1862. And he was wounded in battle on the 7th, and on the 9th he died. Now, his father was actually the governor of Virginia from 1856 to 1860, so he was a pretty important guy. Well, you know, he saved his son's haversack, and that got donated to the Museum of the Confederacy. And here they open this box and they find tablets, and they're like, oh, let's take it to Bob, see if we can find drugs in there. So they brought it over, and we took we didn't want to touch those tablets. I mean, you know, you look at them, they're pretty fragile, it looks like already. We took a minuscule amount of the powder in the box, add a couple drops of methanol, ran it on the DART, and got a beautiful peak of morphine. 150-year-old morphine, still sticking around. That was pretty darn cool. So, with that, all my kids, and of course Chip, all my kids, they're all my kids. I wouldn't be here without them because they've been the light of my life and keeping me busy and trying to do different things and have fun like that. So ask me questions. Yes, sir.
Does that have to be modified with the TLFMS, or do they come as a unit?
The ion sense people will. They're to the point now where they'll make a DART to interface with pretty much any API instrument. They also have Photonis now has one that's a DART on an IMS that's just being presented out here at the show. There's also, the ion sense people have now put a DART on an Agilent, either 5973 or 75, if you've been to their booth and seen that. So there's other ways to do DART now. Any other questions? Yes, sir. Yeah. It was actually nitroglycerin plus NO3 minus. So actually a hunk of it was falling off and recombining with another, essentially deprotonated molecule, and then that was what we saw. And it was incredibly consistent and, just a beautiful spectrum. So, yeah, the DART is kind of like a thermos, how does it know to keep things hot or cold, We always wonder about that. You take salvia and take a methanol extract of plant material, and you get the salvinorin A. It's just this beautiful peak. And amongst all the other stuff that's in that plant material, here the drug of interest pops right up. So it's really kind of cool to see that thing. And we're always surprised and somewhat shocked, and then we have to sit there and scratch our heads and wonder what we've just done. So, anybody else? All right, thank you, everybody.